Today I'm going to be talking about basic issues in experimental design. Specifically, we'll be talking about the four criteria that you have to have in order to be able to say cause and effect, which is kind of the whole purpose of an experimental design, to be able to have causal interpretability. In addition, I'll talk a little bit about two forms of validity that we haven't talked about yet, internal versus external validity. And we'll talk about what parts of your study those relate to and why they're important. Okay, so before we do that, just a real quick review of independent and dependent variables. Ideally, these are things that you already understand from like an intro to psychology class. And it can be sometimes hard to identify these, but hopefully I'm going to give you a couple pieces of information that should make it easy to identify these in experimental designs at least. So the independent variable. Two ways to kind of identify the independent variable. This is the one that the researcher manipulates in an experimental design. Okay, it's the one that the researcher controls. The other way to think about this is the causal variable. This is the variable that's going to cause changes in the other variable, the dependent variable. So just a real quick example to go through here. So I want to know, does media violence exposure cause increases in levels of aggression? And there's lots of ways I could design this, but what I want to do is I'm going to expose half of my participants to watch a 30-minute non-violent video clip. The other half of my participants are going to watch a 30-minute violent video clip. Then later on I will measure their level of aggression in some way. Okay. In this example, I'm manipulating level of aggression, or level of violence in those video clips. Some are getting a non-violent video clip, some are getting a violent video clip. Because I'm manipulating level of violence in those video clips, that's my independent variable. I'm assuming that whether my participant saw a violent video clip or a non-violent video clip, that will cause changes in their level of aggression. Now, one thing that's important to figure out though in a study is, how do we know if our independent variable manipulation was successful? How do I know that the people who watched the violent video clip experienced that as being more violent than the people that watched the non-violent video clip? Well, this is one advantage of using manipulations that have been previously used in existing research, is that they've already worked in other research studies, so you can be fairly certain that they should work in your study. But sometimes you want to double check that. And especially if you've created a manipulation of your own, you need to make sure that it's effective. And one of the ways you do that is you conduct a manipulation check. This can either be done in kind of like a little pilot study that you do before your real study, or it can be done during the real study as well. But basically, you want to make sure that participants experienced the conditions of the independent variable differently. That's what a manipulation check does. It makes sure that your participants can tell the difference between those conditions. So in this example with media violence, one thing that I could do is have a group of people watch the violent video clip, and then another group of people watch the non-violent video clip. And then after they watch it, I just ask them to rate the violence in the video clip. You know, how violent was it on a 1 to 7 scale? Okay. Ideally, what I want to see is that the two groups differ significantly in their ratings. So let's say the average of the people that watch the violent video clip, they're on average rated a 5 on my scale. Whereas the group that watched the non-violent video clip, on average, let's say they scored a 3. So then I'm going to use a statistical test, a t-test, to see if 3 differs from 5 significantly. If it does, great. I can say that the two groups experienced the video clips differently, that my manipulation was successful. Okay. If they weren't different enough, let's say the nonviolent group scored a 4 on average, violent group scored a 5, I compare those two and that's not significantly different. Then I would know that my manipulation isn't strong enough. There's not enough violence in the violent video clip to differentiate it from the nonviolent video clip. My manipulation's a failure. Okay. This is important to know because anytime you run a study, there's always the chance that you don't find anything. We call that null results. Okay. If you find that the two groups didn't differ, then you have to try to figure out why that happened. Well, one of the things that you should think of immediately is, was my manipulation successful? If you do a manipulation check, you know whether your manipulation was successful, and you can eliminate that as a possible explanation for why your study didn't work. So that's why this is important. Okay, the other variable is the dependent variable. This one is always measured in an experiment. So the researcher doesn't control this, they just measure it. So in this example, it would be aggression. Researcher doesn't control their participants' level of aggression, they just measure it later in the study. The other way to identify the dependent variable, this is the effect. This is the thing that changes in response to the independent variable. In other words, participants' levels of aggression should depend upon whether they were exposed to the violent video clip or the non-violent video clip. Okay, it was being affected by the independent variable. Okay, so if we're going to run an experiment, the real reason we run experiments is to get at cause and effect. And experiments meet these 4 criteria for causality. These are the 4 things that we have to have before we can say that one variable caused changes in the other variable. The first thing is covariation. It's just a fancy way of saying that the variables must be related. Our independent and dependent variable have to be related. Okay. Now, we've talked about this before, that correlation doesn't mean causation, and that's true, but in order to have causation, you've got to have a relationship between the variables. So this is kind of convoluted, but it basically means that covariation or a relationship between variables, that's not sufficient by itself to say causality. That's why we say correlation doesn't mean causation. But correlation or covariation between the variables is necessary. It's one of the conditions you've got to meet in order to have causation. If your two variables aren't related at all, one can't cause changes in the other. So covariation just means that we've got to have a relationship between our independent and dependent variable in order for the independent variable to cause changes in the dependent variable. So that's one condition that we have to meet. We also have to manipulate at least one of the independent variables before we measure the dependent variable. So we manipulate the independent variable, we then later measure the dependent variable. This is necessary to infer the causal time sequence. In other words, this is necessary to show that the cause occurred before the effect. If all we did was measure both the independent and the dependent variable, we can't infer the causal time sequence. This is the problem we have with correlational studies. Remember, this is that directionality problem. Even if we can show that these two variables relate, they're correlated, we don't know, is it variable A that causes the changes in variable B, or is it variable B that causes the changes in variable A? We don't know the direction of the cause, but if we manipulate the independent variable, we can establish that that's the cause because that was manipulated before we measured the dependent variable. Third condition, we want to make sure that our participants are initially equivalent. In other words, when we compare the groups of the participants that are in the different conditions of the independent variable. We want to make sure that they're roughly equivalent on all of these individual difference variables, gender, intelligence, how much sleep they got. We want to make sure those things are equivalent across conditions. If we go back to the violent video clip example in aggression, if I have a bunch of people who are highly aggressive, and I have them watch the violent video clip, and then I have a group of people that aren't very aggressive, and I have them watch the non-violent video clip, and then I measure their level of aggression. Okay. Now, if I find out the violent video clip group has higher levels of aggression, I don't know what the reason for that was. Was it exposure to the violent video clip, or is it just the fact that they were already more aggressive to begin with? If I know my groups are initially equivalent before my study starts on aggression, then I can rule that out as a possible explanation for my results. This is another way of saying a confound. A confound is just another explanation for what happened to your dependent variable. In other words, if you have a confound, you don't know, did my results occur because of my independent variable, or was it this other thing that could have led to my results? So we do our best to get rid of those confounds, because if we have confounds, we can't say that it was the independent variable that caused the changes in the dependent variable. We don't know. So we use things like random assignment to help us establish that the groups are initially equivalent. And I'll go through an example of this in just a second. We also want to rule out other extraneous variables. In other words, the only thing that we want to differ during our study between our two groups is the independent variable. That's the only difference we want between those two groups. If I'm running this video clip study, one group's going to watch the violent video clip, one group's watching the non-violent video clip, and then I'm later measuring aggression. If the group that's watching the violent video clip, if they're in a room that's like 85 degrees and it's really hot, the non-violent video clip group is in a very comfortable room. And I get my results and I find out the video clip group, the violent video clip group, scored higher on aggression. I don't know what the reason for that was. Was it the violence in the video clip, or was it because when their room was so hot it made them angry, and that anger caused the higher level of aggression? That would be an extraneous variable that I'm not controlling. So I want to make sure the temperature in my two rooms that people are watching the video clips in is identical, and I'd want to make sure the setup of the two rooms is the same. That would be controlling other extraneous variables. Once again, we do this to rule out those alternative explanations for our results, confounds. So if you design an experiment that meets these conditions, you can show that the independent and dependent variable are related. You've manipulated your independent variable before you've measured your dependent variable. You've used random assignment or some other technique to make sure your groups are initially equivalent at the beginning of the study. And then during the study, you've ruled out these extraneous variables. You can then say cause and effect. Okay, so when we go back to that kind of evidence causality, this is what allows you to say cause and effect. It's meeting these four conditions. Okay, so let's go back to validity. I'm going to talk about two different types, external validity and internal validity. External validity is related to your sample. It's how your participants were selected and who's in your sample. We've talked about this before in the sampling lecture. We have probability sampling techniques that give us representative samples, and we have non-probability sampling techniques like convenience samples. Okay, external validity is all about, can I generalize my results beyond my sample? So if you've used a probability sampling technique, you've used simple random, you've used cluster or stratified, you can generalize your results beyond your sample. Okay? We would then say that you have higher external validity if you've used one of those sampling techniques. On the other hand, if you've used a convenience sample, which is a non-probability sampling technique, we don't know. We don't know necessarily if your results will generalize. So we would call that having lower external validity. So once again, this is all about, can I generalize beyond my sample? Okay. Now there's one specific kind of subtype of external validity. It's called ecological validity. And this is all about, when I run my study, do the results of my study represent how things work in the real world? Okay. So oftentimes people will argue that, well, if you ran your study in the lab and it was very controlled, it's got lower ecological validity because it looks less like how things work in the real world. Okay, so let's say I run a study where I'm looking at aggression once again, and I'm measuring people's level of aggression. And one of the ways you could do that is tell people they're playing a game, a competitive game, versus another person. And when they win a round in that game, they get to deliver an electric shock, supposedly, to the other person. And we probably really wouldn't do that, but they think they're delivering an electric shock. So they press a button and they can deliver, let's say, anywhere from 1 shock to 5 shocks to the person. And they determine how many shocks they want to deliver. Okay, that would be one measure of aggression. An aggression is basically intention to harm the other person. And the idea is that the more times you press that button, the more aggressive you're being. That would be one operational definition for aggression, is the number of times you press the button to deliver shock to this other person. But what about the ecological validity of that? Does that represent how we show aggression in the real world? Not really. We don't. It'd be really cool if we had a buzzer we could press to shock a person when we were angry or wanted to be aggressive. That's not the way things work. So it's fine for showing cause and effect and studying aggression, but a critic could argue that it has low ecological validity, that doesn't represent how we display aggression in the real world. Oh, let me back up and say one more thing about external validity. So we talked about different types of evidence in a previous lecture, that we have frequency evidence, relational or associative evidence, and then causal evidence. External validity is going to be most important if we're looking at frequency type evidence. So, what's the current satisfaction level with the president? Okay, if you really wanted to evaluate that claim, they better have high external validity in that study. They should have used a probability sampling technique. If they didn't, you shouldn't really pay attention to that frequency type data. If our focus, on the other hand, is more on associative or causal evidence, external validity isn't all that important. It really doesn't matter as much how we obtained our sample, because we're more interested in whether variables are related and if they're related in a causal way. If our focus is on being able to establish cause and effect, we care less about external validity. What we care more about is internal validity. And this is because it's related to the design of the study. So external, related to how we've acquired our sample and who's in our sample. Internal validity is related to the design of our study. Experiments have the best internal validity. Case studies, naturalistic observation, correlational studies, quasi-experimental studies, those all will have lower internal validity than an experiment. And there's a couple different ways of thinking about internal validity. One way to think about it is, do I have causal interpretability? In other words, if you go back to one of the previous slides, those 4 criteria, in my design, am I meeting those four criteria? Okay, once again, if you've got an experiment, you're probably meeting those four criteria. If you've got a frequency type study or a survey or a correlational study, because you're not running an experiment, you're not going to have causal interpretability. Right? So that's what internal validity is about. If you run an experiment, higher internal validity, higher likelihood of causal interpretability. If you run a non-experimental design, that lowers your ability to have that causal interpretability. You have lower internal validity. Another way of thinking about this or talking about internal validity, can I say my independent variable caused the changes in my dependent variable? If you can, you have high internal validity. And your ability to say that goes back to those four criteria and ruling out confounds. On the other hand, if you've got confounds in your study, and so you can't really say it was your IV that caused the changes, it could have been one of these confounds, that lowers your internal validity. Okay, so internal validity, this is more about causality. Can you say that the independent variable caused the changes in the dependent variable? Now, as I mentioned before, if you have confounds, you can't really say that it was the independent variable or the confound that caused the changes in the dependent variable. And confounds are bad, but so is error. And we need to be careful on how we use this language because they mean specific things, and each thing refers to different elements. So let me first describe the difference between the two, and then we'll go through a couple of examples. A confound mimics the effects of the independent variable. It's mimicking the effects of the independent variable. So you can't tell, are my results due to the independent variable or are they due to this confound? Another way of saying that is confounds affect the conditions of the independent variable differently. Okay, confounds affect the conditions of the independent variable differently. Right, so that's a confound. It mimics the effects of the independent variable, affects the conditions differently. Error, on the other hand, in general, error affects the conditions of the independent variable about the same. Okay, there might be slight differences, but it's about the same. So let me give you a couple of examples of this. So let's say we're interested in this question, do study guides help improve exam performance? And let's say based on previous research and theory, study guides should help exam performance. So if we have students who get a study guide, they should do better on an exam than students who don't have a study guide. It might help focus their studying or help them test their knowledge, whatever. So what we're going to do is we're going to have two classes, same material being covered in both classes. One class is going to get a study guide for the first exam. The other class isn't going to get a study guide. And then we're just going to compare their first exam scores. And everybody's taking the same exam. Okay. So I'm going to throw a couple of different problems at you that could come up in this kind of a design. And try to identify whether that's a confound or whether it's error. So the first thing, let's say we have different teachers teaching the two classes. Okay. And we run our study and we get the results and find out the study guide group does better on the exam than the non-study guide group. Are the different teachers in the class, is that an error or is it a confound? In this case, it's a potential confound. It might mimic the effect of the independent variable or affect the conditions of the independent variable differently. Okay. In this specific example, in order for this to be an actual confound, think about which teacher would have to be better quality. Would it be the teacher in the study guide group or the non-study guide group? Okay. In order for this to be an actual confound and mimic the effect of the independent variable, the teacher in the study guide group would have to be the better teacher. Okay. That way, when we get our results, we don't know, is it because the study guide group got a study guide and that's what led them to score better on the exam? Or was it the fact that they had the better teacher? Okay. If they had the worst teacher, that would not be mimicking the effects of the independent variable. It would actually be going against the independent variable. And in that case, it technically would not be a confound because it can't explain our results. Okay. So in order to be an actual confound, it's got to mimic the effect, remember. Let's say on that exam there's a bad test question. Is that going to be a potential confound or is that error? That's going to be error because both groups, the study guide group and the non-study guide group, are going to be affected about the same by a bad question on the exam since everybody's taking the same exam. Okay. What about time of class? Potential confound or error. If one class is taking, or the study guide class is at a different time of day than the non-study guide class, that's a potential confound. And once again, in order to be an actual confound, the study guide group is going to have to be at a better time of day. So maybe the study guide group is at 11 o'clock in the morning, which is closer probably to where most college students are kind of at their cognitive peak. Whereas the non-study guide class, they might be at 8 o'clock in the morning, which most college students or students of normal college student age, traditional students, that's not going to be their cognitive peak at 8 o'clock in the morning. It's later in the day. So that would also be a potential confound then. All right, so that's the difference between errors and confounds. Confounds affect the conditions of the independent variable differently. Error affects them about the same. Another way of differentiating the two, they're both bad, but they're bad for different reasons. And it goes back to this formula that we'll keep coming back to over the course of the semester. That the total variability in a study equals systematic variance plus error variance. So if we stick with our study guide example, the differences between the two groups, that would kind of be our total variance. So the difference between the study guide and the non-study guide group in their exam performance would be kind of the total variance. Part of that is systematic. In other words, it's variance ideally we can explain in one way or another. But there's also some of the class differences that we might not be able to explain. It's error. Okay? Now, part of the differences between the two groups that's systematic and that we can explain is due to our independent variable, our treatment. In this case, whether or not students got a study guide. So differences between the two classes, part of those differences we can explain because it's based on did you get a study guide or not. Okay, that's ideally what we want. We want all of the systematic variance to be due to the independent variable because we can explain that. The problem is that if we've got problems like two different teachers teaching the two classes, we have a potential confound because those two teachers offer another explanation for systematic variance and a reason for why the two classes differ in their exam performance. It's a potential confound. Are the results or the differences between the two classes on exam performance due to one getting a study guide and the other one not? Or is it due to the fact that one teacher in the study guide group is better than the teacher in the non-study guide class? Okay, so we don't know our results due to the independent variable or the confound. This is why confounds are bad. It makes it so that we can't tell what the reason for our systematic variance is. Now, once again, if you run an experiment and you use random assignment, control other extraneous variables, you've eliminated the confounds. You got rid of all this. And therefore, systematic variance is just due to treatment or the independent variable. And that's what we want. So we're trying to rule out confounds with the design of our study. Error variance, on the other hand, this is bad, but not because it's it makes it difficult for us to interpret our results. It makes it difficult for us because it might hide actual differences between the groups. In other words, in reality, it might be that the study guide group scores higher than the non-study guide group. But if our exam, there's just a ton of bad questions on that exam, that creates error variance, and it's going to make it more difficult to tell if our two groups actually differ or not. If the exam is kind of worthless because it has so much error in it, it's not a good measure of students' knowledge and understanding of the material. And therefore, the study guide, whether they got a study guide or not, it's harder to tell. Okay? But if we gave them a really good exam that had all good questions measuring knowledge, and we minimized error variance, it'd be easier for us to tell whether the study guide group performed better than the non-study guide group. Okay? So error variance, the more we have, it makes it harder to tease apart whether there's a difference or not between our groups. Okay? Another way of thinking about this, kind of an analogy, is if you're ever watching TV, and especially in Wyoming, the wind comes up. And if you've got satellite TV especially, the wind might kind of move your satellite dish. So it's not in perfect, it's not connecting perfectly with the satellite. You get those little squares, it kind of digitizes your screen, so it makes it hard to see what's on there. That's kind of what error's doing. So if you're watching TV and trying to see what's going on in the episode that you're watching, and the wind comes up, and it creates those little squares on the screen, that's what error is doing. It's making it harder to see what's there. You can't tell what's going on in the screen. If you're watching like a football game, you don't know who has the football. It makes it really hard when the wind comes up to tell who has the football. That's what error variance is doing. It's making it hard to tell if there's real differences between our independent variable conditions. Okay, both confounds and error variance are bad, just for different reasons. Remember, confounds are part of systematic variance, whereas error is part of error variance. That's another way that they differ. Okay, so going back to internal validity, how do we maximize this? Maximize internal validity by running experiments in a very controlled setting, like a lab. It's very artificial, but you control everything. And that maximizes internal validity. You're ruling out as many confounds as possible. The problem is that, and Leary talks about this in your textbook, this creates a trade-off perspective or an experimenter's dilemma. When we maximize internal validity by running studies in the lab, very artificial, we control everything, that slightly decreases our external validity, specifically kind of this ecological validity. We are less representing how things operate in the real world because it's so artificial in the lab. So maximizing internal validity kind of lowers external validity a little bit. And the opposite also kind of occurs. When we try to maximize external or ecological validity, it slightly lowers internal validity because we usually don't control quite as many variables then. So the question is, the trade-off perspective or the experimenter's dilemma is, what should you do? And there's kind of two responses to that. One, the first response is what Leary says in your book. He says, look, we usually care about cause and effect, so just maximize internal validity. Who cares about ecological or external? And that's fine. But usually researchers conduct a program of research. They do multiple studies. And yeah, you can't maximize internal and external validity both in one study, but you can maximize them across multiple studies. So the other solution is run a couple of studies to maximize internal validity, to establish, yes, there's a cause and effect relationship between these variables. After you've run studies to maximize internal validity and show the relationship, then run a couple of studies to maximize external validity. Does that cause and effect relationship work even when we kind of make things more realistic? Okay, So you can't maximize both in one study, but you can maximize both across multiple studies. All right, so let's go through some examples of eliminating confounds here. And if you've taken my Intro to Psychology class, I apologize because I used the same example in that class. But let's say we want to know, does Red Bull actually give you wings? And we contact Red Bull. They tell us what they mean by wings is that it increases, concentration, cognitive performance. Okay. In addition, they tell us what the one ingredient in Red Bull is that supposedly has that effect. So what we want to do is we want to expose some students to that active ingredient and other students not. So we're going to manipulate whether they get the active ingredient or not. That's our independent variable. The dependent variable then is we'll just give them a psychology test, because if that active ingredient really improves cognitive performance and concentration, it should help them perform better on an exam. So our dependent variable is going to be score on a psychology exam. And we need a large group of people. So let's say we're going to do my Intro to Psych class. And so I give half of the students, when they come into the room, I give them real Red Bull. The other half of the class, I give them some water to drink. And then a little bit later, I give them the exam, and then I compare the scores on the exam, the Red Bull group to the water group. Okay, and I find out the Red Bull group does better on the exam. Can I then conclude that Red Bull gives you wings? Okay, see if you can think of other confounds in that design that I haven't controlled. Okay, one important confound is people know what they're getting. If I hand you a can of Red Bull or water, you know what you're getting. And it could be that people know that Red Bull's supposed to give them wings, and just that expectation of getting wings helps them perform better on the exam. So now I have a confound. I don't know, was it the active ingredient or the expectation that they should do better that led to their performance? Other problems, taste. Water and Red Bull taste different. And I don't like the taste of Red Bull, but let's assume that people like the taste of Red Bull. In that case, taste is a possible confound, because it could be that when you drink something that tastes good, that puts you in a better mood, and then that could influence your exam performance and help you if you're in a better mood. Whereas you don't get that good mood if you're drinking water. Okay, so that would be another potential confound for my results. So I've got to control these extraneous factors. So what I would need to do is hire a chemist to create real Red Bull and fake Red Bull. And the only difference between the two is whether or not it has that one active ingredient, my independent variable. Real Red Bull has it, fake Red Bull doesn't. They taste the same, they look the same. We're going to put them in the same container so students don't know if they're getting real or fake Red Bull. So I've eliminated those other extraneous factors, all those confounds, right? So that's one key I've got to do here. I've got to hold those other factors constant. The only way I want my two groups to differ is on whether they got the active ingredient. So I've got to control the taste, I've got to control their expectations, all of those things. Okay, that's great. But it could be that my two groups differed from the very beginning. What if, just by a fluke, I assigned all of the people who studied really hard for the psychology exam to the Red Bull group, and the people that didn't study as hard went to the fake Red Bull group? Okay, that would be a problem because I don't have initial equivalence. To get that initial equivalence, I need to do random assignment. Okay, another problem, let's say if I was lazy and I just said all the women are going to get Red Bull, all the men are going to get fake Red Bull. I have a confound because my groups are not initially equivalent on gender. So now gender is a potential confound for my results. But if I randomly assign participants, I draw names out of a hat. First name gets real Red Bull, second name fake, third real, fake. If I do it like that, my gender balance between the two groups is going to be the same. Have the same number of men in my two groups, same number of women. And now if I get my results that the Red Bull group does better, it can't be due to gender because gender is equivalent across the two groups. Random assignment should make all of those other individual difference variables roughly equivalent as well. So how prepared students were, my two groups should be about the same on preparation or sleep or whether they're sick or not, because that could influence concentration. So if I do both of these things, I can show the four conditions needed to establish cause and effect. I can show that the independent and the dependent variable relate. Specifically, I could show that the Red Bull group scored higher than the non-Red Bull group on exam performance. That would show that there's a relationship between my variables or covariance. I've manipulated my independent variable, whether they got the active ingredient or not, before I've measured the dependent variable, exam performance. I've controlled other extraneous factors, making sure the taste is the same, students' expectations about what they're getting is the same, and I've used random assignment to get initial equivalence. If I do all of those things and then I find out the Red Bull group did better, I can then say, yeah, Red Bull gave you wings. I can say cause and effect. Okay. Another example of this, of a confound, you might have actually seen some of these commercials on TV where they do these magnetic bracelets. They're supposed to have all these great effects. But let's say you're going to get one of these magnetic bracelets, and we're manipulating whether there's real magnets in it or not, and it's supposedly going to influence how much pain a person experiences. Okay. So our independent variable here is whether you're getting the real bracelet, the real magnetic bracelet, or the fake one. Our dependent variable, we're going to have you do some rating of pain at the end. Well, if during the course of the study, and this is especially problematic when the researcher knows what conditions the participants are in. Let's say this researcher is working for the magnetic bracelet company, and the people that get the fake bracelets, they're really rude to and mean. The people that get the real bracelets, because the researcher knows they're the real thing, they're much nicer to them. And then at the end, we find that the real bracelet group has lower pain. Well, the problem is we've got a confound. We don't know, are the results due to the magnetic bracelet, or are they due to the way the researcher treated the participants? And this is why we typically like to, the person running the study or interacting with the participants, we typically like to have them be so-called blind to condition. That way they can't systematically affect or influence the participants in this way. So if this researcher was blind to conditions, blind to condition of the independent variable that the participants were in, they wouldn't have this effect on people because they wouldn't be able to affect people in a systematic way because they wouldn't know which condition people were in. All right, also want to point out important differences between random assignment and random sampling. Random assignment, remember, this is one of the necessary criteria to have cause and effect because this gives us initial equivalence. All right, so this is all about who's in which independent variable condition. Random sampling, on the other hand, this doesn't have anything to do about cause and effect. This has to do with who can we generalize the results to. If you use random sampling, you can generalize your results from your sample much better than you can if you used a convenient sample. These two things, they sound similar because they both have the word random in them, but they're different for reasons. They differ in terms of which validity they relate to. So remember, internal, external validity. Random assignment helps us with our internal validity. It's irrelevant for external validity. The opposite is true of random sampling. Random sampling is all about external validity, has nothing to do with internal validity. So, if someone says, well, you didn't use random sampling, so you can't say cause and effect. Nah, that's wrong. because random sampling has nothing to do with cause and effect. It has all to do about, can you generalize your results when you're done to the population of interest. It also relates to which designs are important or which types of evidence we're dealing with. Random assignment is important for causality type evidence. So the design that's going to be most helpful with that is going to be experimental designs that will have higher internal validity than non-experimental designs. Random sampling and generalizing your results, that's more important for frequency type evidence or polling research, where the goal is to be able to generalize your results and say something. What is the current approval rating of the president? Random sampling would be important for that. Random assignment would be irrelevant for that. Okay, so two completely different things. They relate to different types of evidence. They relate to different types of validity. All right, random assignment, once again, it's important for internal validity. You will sometimes see non-random assignment or self-assignment. So it might be, if we want to run a study comparing cognitive therapy to some humanistic therapy in the treatment of depression, and we go through the IRB, and the IRB says, well, you think cognitive therapy is going to work much better than humanistic in the treatment of depression. If that's true, maybe we should, it may not be ethical to force random assignment onto that, because some people would be getting the less effective treatment. So maybe the IRB says you've got to let people pick which type of therapy they want to go into. Okay, that's problematic because now if you let people pick, what you've done is, remember, random assignment's important for meeting that criteria for causality of initial equivalence. If you do non-random assignment by allowing participants to select which therapy they go into, you've got potential confounds now, because your groups may not be equivalent at the beginning of your study. It might be, and I'm making this up, it might be that you're more intelligent folks, or folks that are more savvy about therapy, they self-select cognitive therapy because they know that research shows that it's pretty effective. Whereas people who know less about therapy choose the humanistic therapy. And now you don't know when you get your results, and if you find the cognitive therapy lowers depression more than humanistic, you don't know. Is it the therapy that mattered, or is it the self-selection? That the more savvy, the people that knew more about therapy entered into cognitive therapy. So you don't know, is it, if you know more about therapy, maybe it's more effective, or was it the therapy type? So you've created a confound anytime you have non-random or self-assignment. All right, and relating the different types of validity that we've kind of talked about so far over the semester to different parts of your experiment, or not your experiment, of your study. So external validity, remember, that deals with your sample. How did you acquire your sample? If it's a convenient sample, that lowers external validity. Probability sample, that raises your external validity. Construct validity. Are you actually measuring the construct you intend to measure? If you want to measure depression, is the scale you selected, does it actually measure depression? So this deals with measurement. Construct validity. Are you measuring what you intended to measure? Internal validity. Can you say that it was the independent variable that caused the changes in the dependent variable? Do you have causal interpretability? That depends upon the design. Experiments, higher internal validity than non-experiments. And then another type of validity that I haven't mentioned yet, it's called conclusion validity. In other words, when you analyze your results, did you draw the correct conclusion? And this is based on things like, did you use an appropriate statistical test? Did you interpret your results correctly? So those things relate to conclusion validity. If you interpret your results correctly, you use an appropriate statistical test, you have higher conclusion validity. If you used a statistical test that shouldn't be used with that kind of data, or you misinterpreted the output from SPSS, that lowers your conclusion validity. Okay, going back to the steps kind of the research process, relating this to validity and a research report or writing things up. In your method section, the materials that you use, so the manipulations, the scales that you use, are you manipulating or measuring the construct you intend to measure? That's how we are relating things to, construct validity. Okay, if you're using existing materials, vignettes, scales, you probably are going to have okay construct validity. If you've created something on your own and you've never tested it before, you might have lower construct validity. We don't know if your manipulation or your items are tapping the construct you intend to measure. Also, external validity, this has to do with how you've obtained your sample. Did you use a convenience sample or did you use a probability sample? If you used a probability sample, you definitely want to mention that in your participants section because that required more effort of you as a researcher. So you want to get credit for that. And then the procedure section of the methods section. How did you conduct your study? What kind of a design did you have? That relates to internal validity. Obviously, if you had an experimental design, you have higher internal validity than if you just had a correlational design or if you did a survey or a poll of people to get frequency data. Then you have lower internal validity. The results section, remember this goes to the statistical analysis. How did you evaluate your data? If you use an appropriate statistical analysis, then you have higher conclusion validity. And did you interpret the results correctly? If you did, you have higher conclusion validity. Inappropriate statistical analysis or you misinterpreted the results of your statistical analysis, that will lower your conclusion validity. Okay, so that's it for today. We talked a little bit, did a quick review of independent and dependent variable, and then spent the rest of the time talking about kind of the 4 criteria to be able to say cause and effect, and that relates to internal validity. We also talked about external validity, which is more based on your sample, and how you've acquired your sample. Okay, all right, that's it for this lecture.